Hi again. So today we're going to talk about how we can make ionic structures in 3 dimensions and how we can look at the three-dimensional packing or the solid state structure and how we can interpret that to figure out what the formula of the ionic salt actually is. Okay, so just to recap on ionic bonding again. So this is a multi-step process. So we have elements that are unhappy because they either have too many, like in sodium atom's case, too many electrons, or too few, like chlorine. And so chlorine would desperately like to accept one more electron to have a full outer octet, 8 electrons, and sodium would love to get rid of this one electron, and so it can undergo a 1 electron transfer. In the process, sodium has a complete outer shell, but also gains a positive 1 charge because it has 1 too few electrons. Chlorine gains 1 electron and completes its outer shell, becomes stable, but becomes negatively charged. And of course, because this is a positive and a negative, these are attractive forces, and these two atoms are going to try and stick together to form an ionically, electrostatically charged bond. Of course, we know that in the macroscopic view of what a salt crystal is, that it is actually composed of many, many, many ions, not just simply one sodium atom and one chloride atom. And so after the electron transfer has happened and after they pair up, these begin to aggregate, and so they actually get larger and larger and larger, forming this crystal lattice. This crystal structure, or the solid state structure of interspersed positive and negative charges, which are helping basically stabilizing the ionic structure. Now, one of the things we want to do is we want to be able to look at a structure like this, and we want to be able to pull out the most pertinent information. And for that, really wanted the empirical formula. And the empirical formula is the simplest positive integer ratio of atoms present in a compound. So if we were to look at this repeating lattice, we would say that although that maybe there is 10,000 sodium atoms, sodium, there are an equal number of chloride atoms, and so the simplest positive integer would be the most reduced form, which would be a 1-to-1 ratio, sodium chloride. And hopefully you can kind of see that in this representation, that whether or not that you represent this in a 2-dimensional way or in a more realistic 3-dimensional way, you're still going to always end up with a 1-to-1 sodium to chloride ratio as the empirical formula. One of the really neat things about crystal structures is that in many instances, the macroscopic view, that is the human view of the object, can and sometimes does imitate what the molecular crystal structure. So sodium chloride crystals form these nice cubic structures, and in many cases you can get these square or cubic-like salt crystals as well that directly represent the manifestation of how the atoms are packing in the solid state. So when we're talking about the packing these atoms together, and once again, atoms are very spherical-like, and we're talking about positive and negatively charged ions that are electrostatically attracted to one another, so that they have kind of glued to one another. But the thing is that there's actually quite a few different ways to pack spheres. On its surface, you think when sodium chloride, where everything is in a nice perfect square, but even if you were to look at something like how one stacks oranges at a supermarket, you can see that there are actually quite a few arrangements where you can get stable kind of spherical packing systems, and these are also some representations of how you can stack different spheres together in the solid state. And so let's introduce some new topics here, new concepts, so that what we can do is we can look at a packing system, how the spheres have been all packed up for an ionic compound, and we can ultimately get back to the empirical formula. And so this mineral is fluorite. This is calcium fluoride, and you can see two different representations of this particular molecule in the solid state right here, as well as kind of a more space-filling one right there. It's a beautiful, beautiful blue mineral. And so what we're going to do is we're going to introduce the concept of the unit cell. So if I wanted to just look at a whole bunch of differently packed atoms, and I wanted to figure out what was the kind of the empirical structure of this system, what I would do is I would try and find a unit cell. And the unit cell is the smallest group of atoms from which the entire crystal can be built up by a repetition in all three dimensions. And often when you're looking at a solid-state structure, they will provide you with the unit cell. So this is the repeating unit, and you can have atoms inside the unit cell, this kind of cube, or you can actually have the unit cell cutting through atoms. And so let's do the calcium fluoride as an example. Okay, so we're going to look at this particular unit cell for calcium fluoride, and we're going to start with the fluorine. That's pretty easy. So there are 8 fluorine atoms all inside the unit cell, and so we're going to count all 8 of those atoms. So we have F8, and yes, I know that the empirical formula is right here, and so just stay with me. I know that there's only F2 in this case, but we'll get there in the end. Okay, so let's do the calciums next. And the calciums are a little bit trickier because within this repeating unit cell, the actual cube bisects the calcium atom, so it actually cuts through them. And so we have 8 calcium atoms, and these 8 calcium atoms are sitting on the vertices, or the edges of the cube. And so if we actually look at what is inside the box, only 1/8 of the calcium atom is inside the box. And so if we have 8 calciums, each of which is only contributing 1/8 of its volume, this is as a total going to contribute 1 calcium inside the unit cell. We also have these 6 calcium atoms which are sitting on the faces, and so there's one behind I can't really get to. And so the 6 calcium atoms that are sitting on the faces are cut in half, and if we could rotate this we could see it pretty clearly, although you can kind of see it right here at the top, that the calcium is cut in half, so that each of these calcium atoms is going to provide 1/2 of its total atom volume to the unit cell. So if we have 6 calcium atoms and each one's producing half, that's going to give us a total of 3 calcium atoms. And so if we look at which atoms are inside the unit cell, I think we would say something like calcium 4, fluorine 8. And of course, this is the smallest repeatable unit in this crystal. This is not quite the empirical formula, but we're getting really close now, especially if we didn't know right off the bat that this was the structure. We could reduce this further. This is a common denominator. We could divide this by 4 and ultimately get down to the empirical formula of CaF2, or calcium fluoride. Let's do one more. Let's do rutile, which is a titanium oxide. In this particular case, I'm not going to share with you what the formula is off the bat, but I am going to give you the unit cell. You can actually see here, this is rutile crystals that have actually grown inside quartz, which is a silicon oxide, and it's really, really quite pretty piece of mineral art. And so in this case, the titanium is in gray and the oxygen is in red, and so let's see if we can't figure this out. So we have, let's do titanium first. So the titanium, in this case, there's one whole one in the middle, and then we're going to have 8 titaniums that are sitting on the vertices of the unit cell. And if we have, each one is going to be providing 1/8 of the total volume of its atom, and so that should equal a total of 1 more titanium atom. Next, let's look at the oxygens. And so we actually have 2 different types of oxygens in this unit cell. We have these oxygens right here, which are completely in the cell, and so we actually have each one counts for a full atom, and then we actually have these four, and they're kind of cut in half. You can kind of really see it right here. This one's been cut in half. Half of it's sticking in the cell, half of it's in the next cell below it. Just like this one, half of it's in this cell, half of it's in the cell above it. And so if we have 4 oxygens, each contributing half of their total volume, that is going to be another 2 oxygens. And so if we were to combine these, we would see this would be Ti2O4, and we would come up with a common denominator empirical formula of titanium oxide, or TiO2, which is the empirical formula for rutile, a beautiful mineral.